Okay, in this segment, I want to show you a really interesting algorithm called a minimum spanning tree, which is very practical, applied to many real world problems that you can model as a graph, and which will be easy for us to understand because it is almost exactly the same as Dijkstra, with just one very tiny modification. So I thought it would be an easy thing to introduce without having to really learn any new concepts or think about things in any particularly different way. So let's take a look at that. And there are two ways to do it. And I'll show you both ways just for the fun of it. And I went through the process of animating them in PowerPoint so that we could go through it pretty quickly. So let me share my screen. So the application is to compute what's known as a minimum spanning tree of a graph. And what that is a subgraph of the graph. In other words, you retain not all, but some of the vertices. And the ones you choose to retain are such that you can still visit every node from every other node if the graph is connected, let's say. Okay, so you can still get, generally speaking, everywhere that you could get before. And you do it in such a way that you minimize the total cost. So you look at the edge weights and you select the set such that their sum is minimum, and you could still get by a sum path from every node that you could get to before from every other node. Or if you get anywhere in the graph, if the graph is connected, then we just say you could still get everywhere. Okay, so I'm gonna show this in a slide that I borrowed from somebody that just makes it a little bit more real. Imagine, it's still a little artificial, but you can imagine this kind of problem in building networks and networks of computers, networks of cables, or whatever the case might be. In this case, it's roads. So imagine you've got a bunch of houses in a town, and let's say a road is something that just connects any two houses, and their roads have repair costs associated with them, and those repair costs are encoded as the edge weights between any pair of houses. Okay, so the idea is that you want to build this road system so that everyone stays connected. In other words, you can get from every house to every other house, not obviously directly. That would be what's called a complete graph, but there's some set of edges that gets you from some place to the other place, but that the total repair cost is minimized, so that when you sum up the edge weights, you get the minimum possible value. And of course, that's a criterion for determining which of these to remove and which not. So let's say if you can get from here to here in, well, let's find a better one. If you get from here to here in, so from here to here in these two hops, which cost 13, then you can go directly for one, then you might be able to eliminate one of these because there are other ways to get from here to here. Okay, let's say from here to here to here, and whatever. We'll see what happens. But that's the idea, is that you're eliminating ones that still keep you connected, but which ultimately are going to give you a minimum total cost. Okay, and so when you turn that into a graph problem, obviously we think of the vertices as the houses, the edges of the roads, and the weights as the repair costs. And we want to find a subgraph that connects all the vertices. So we want to find a subset of vertices such that a subset of edges such that these are all connected, and such that the total weight is minimized. Okay, the sum of all the weights of the existing edges. So let's do it. There are going to be two algorithms. I'll show you Prim, and then I'll show you Kruskal in the next segment. Prim and Kruskal both work with undirected graphs. They can be either weighted or unweighted, but they're more interesting when the edges are weighted. And they're just like Dijkstra in that they're greedy algorithms. So you solve a local optimal problem, and you build up the global optimal solution out of the small optimal solution of the many subproblems that comprise it. Okay, so it's going to be actually just like Dijkstra, except the distance that we keep is not going to be the aggregate distance from any one vertex to another, but it's going to be just the distance from the parent vertex. Okay, so let's take a look at it. Let's start with D like we did with Dijkstra, and let's have our chart. And chart is, are you in the set of vertices which have been fully processed and don't need to be visited. And that's, again, how we build up the solution. Nobody's in that set K. And then one by one, we put people in the set K by solving a local optimal problem. And just like before, we keep track of the parents, and we pick the next vertex based on the next closest place you can get. But we do not increment, we do not keep the total path length from the initial vertex, we just keep the path length from the parent. So let's see what that looks like. We start with D, so D is now in the set K of process vertices. It has no parent and its distance of self is 0. So we first ask, where can you get from D? Just like with Dijkstra, we can get to C, E, F, and G, and we know the weights of those edges, and we just put them in our table, okay? And we mark who the parent is, nothing new. And then we do the same thing we did with Dijkstra. We say, what's the next shortest path? It's G. So we're going to consider G true. It's processed. And we're going to ask, where can we get from G? Okay, so G is processed. And from G, we can get to H and we can get to E. Note that we can get to E in 7. So 7 is going to replace 25 here, okay? And again, it's not going to be the total distance from D to G to E, but it's just going to be the distance from G to E that we encode here. That's what's different about it, okay? So we are going to change that, and we could also get to H, which is 3 away from G. So you don't put 5 in H, you put 3, the distance from the vertex, the distance from the vertex which discovers it, okay? So H has 3, E has been updated to 7. Okay, so it's the same algorithm, except for the fact that you do not add the distance to the back to the source. Okay, so then we say, okay, what's next? We could do either C or H. So I say, let's do C. So C is done. Where can you get from C? You can get to B and F. So we'll put B and F in the table. And notice that each time I color a vertex processed, so D, C, and G are processed, I color red the edge that got us there, okay? So that edge you might now predict is going to be what we retained as the minimum spanning tree, right? So now we look on our list and we could do either F or H. Alphabetically, we'll do F. So now F is processed, and F will get us to E as 2. So that's very important, okay? Wait, we don't have anyone getting to E. Yeah, we have E is 7. So now we have an edge to E is 2. So we're going to replace that. And notice we can get to A in 10, and we haven't had any way to get to A before, right? So now we have 2 and the parent from the parent F. Again, this is from the parent, and 10 from the parent F. Okay, now we're going to look on our chart, and we've got a 2 in there. And so we're done with E. Okay, and where can we get from E? We can get to B in 10, but that doesn't help us. And that's it. So we don't change the table entries at all. And we just look for the next shortest one, which is H. And let's see. So H is done. And from H, we can get to B in 9, which is no better. We get to A in 4, which is better. So we're going to have to update this a 4 and update that with an H. Okay. And now if we look at our table, we're going to alphabetically do A next. And from A, we can get to B in 8. That's no better. So I don't do anything, no changes in the table entry. And then we get to B. And now, if we just look at what I colored in red, boom, there's my minimum spanning tree. Okay, and the total weights sum to 21, and I can still visit every vertex in the graph. So we got rid of redundant, the most expensive redundant edges. And one thing to realize about this, I might have mentioned it, is that there can't be cycles in such a graph, because if you had a cycle, you could just remove one edge of the cycle and it would still allow you to get anywhere. You move the most expensive edge. And these aren't necessarily unique. There could be ties, right? So this gives you one optimal version of a minimum spanning tree. So it's kind of remarkable. That's such a cool algorithm. I'll show you then in the next segment a similar version called Kruskal, but it's going to look at edges instead of vertices. It just gives you a flavor of how these things work.